This video is a presentation of a 3-joint planar robotic arm that was developed as an educational tool and research platform here at Colorado State University for the Electronics and Computer Engineering Department. We'll be going through the development of the arm, why it was developed, and different things that can be done with it now that it is available for people to use. So the motivation behind this is that in robotics education, students often learn the basics of joint control, its trajectories, its position, on simple models, such as the 3-joint planar arm example that's shown on the right. Now that trajectory control is based on trying to control the position of the end of the arm relative to the position of the joints. And so you have a known position of the end of the arm, and you have to try to figure out where the joints should go to get the end of the arm there. And so this is a very classic model. Used often. The 3 joints that are shown by the small circles all rotate in the same plane. Their axis of rotation is all in the same direction coming out of the screen for this video. And so that can create some interesting problems because there's more joints than are needed, and so there has to be an intelligent control. It can't just be pick a spot and find something that works. There's an infinite number of possibilities for every single location, so there has to be some kind of trajectory control. So it works well for robotics students. Researchers also use this to demonstrate some of their ideas. Some of the ideas that have been demonstrated on this platform are fault-tolerant workspaces and kinematic redundancy. I spoke earlier about how there's more joints than are needed. That's what it means when something is kinematically redundant, that it doesn't necessarily need all the joints that it has to accomplish movement in its space. And the example on the right is one of those. It is a kinematically redundant arm. There's been research that shows that given one of these kinematically redundant arms, there can be a fault-tolerant workspace developed, where even if a motor fails, there is some area that the arm can still reach no matter which one of the 3 joints fails. And so that's some of the research that has been done using this exact model, and there is planned future research using similar fault-tolerant methods, which we'll talk about those in the development of the arm. And so this project was to build a physical platform to demonstrate these principles and to test future ideas on for students and researchers. Now, some of the requirements that were asked for this project to allow it to succeed in the spaces discussed is that, first of all, it be easily moved. If it is going to be a demonstration tool, it has to be able to be moved from a lab where it's being stored to a classroom, perhaps even to a different building, or even into a car to be easily transported by vehicle. And so it had to be portable, lightweight, and of a size that it could fit into vehicles. The plane of motion for the arm had to be able to be oriented to be perpendicular to the ground. Now, it doesn't necessarily have to stay that way, but it should be able to operate in that mode. And that is for the failure methods. One of the methods of failure that was asked to be tested was a free-swinging failure. And for that to be tested properly, they wanted the plane of motion to be perpendicular to the ground. So if something fails in a free-swinging mode, meaning there's no torque on it, it can fall due to gravity. So that method was requested. It should be easily seen from a distance away. Say a back of a classroom should be able to easily see the movement of the arm. It should be able to have the motors rotate continuously, 360-degree rotation possible. Now this does not mean that it should be able to rotate continuously forever, just that it can achieve at least 360-degree rotation in any direction. There's limitations such as wire lengths that have to be taken into consideration. The motor's position and velocity should be able to be sensed, so that way the intelligent control can be done. It should be reprogrammable. There should not be a single software function that runs on it, whether that be reprogrammable by students or researchers. Either way is necessary. There needs to be space for future sensors and actuators, for things like braking mechanisms or color sensors or whatever it may be that they may need this platform for use in the future. There should be ports and space available for it. The links between each of the motors should be modular such that they can be easily swapped out or new ones developed if the case may be. And it should be able to simulate both locked joint, where the motor after a failure mode is stuck, and free swing, which we already discussed. So a system overview of the platform, you can see pictures of it both from a front view and from a side view to see the motors. Now the back of it is where all the circuitry is mounted. The mounted base itself is 3 feet by 3 feet plywood that has been used as a stabilizing support. There are feet at the bottom that are used so that it can be oriented, so the plane of motion is perpendicular to the ground. It can also be flat, so the plane of motion is parallel with the ground. Either way will work. There are 3 rotary motors. Each of them has their own torque limitations. They're geared motors with encoders on the back, with a Hall effect encoder. It has Cytron MD10C motor controllers that can handle enough current to support each of the motors. And those motors have a 2.5 amp stall torque, and so the motor controllers are designed for that. The main controller is an Arduino Mega 2560. That gives us plenty of room for ports. The power supply is a 180 watt basic desktop power supply unit. It came out of a Dell computer, and so that has the power requirements that we need both for the motors and for any future actuators or sensors that may come in. And the links are 3D printed out of ABS plastic 3mm filament. So the designs are easily swapped out. They can easily print more links of different shapes or varieties if some are required. And each motor is compatible with all the other linkages, so even the links can be swapped while the motors stay in their places without any effect on the system, other than the length of the links, of course. So the motion control of this is designed for forward kinematics and using a Jacobian matrix to map between the Cartesian space of the end of the arm to the joint space of the motors. And this idea of motion control uses the position and velocity feedback from the joints to be able to plan the next step. And that all uses local control. And now these good design practices are for students using damp least squares, examining the local properties of the Jacobian matrix for exactly where the arm currently is for future planning, and it allows for secondary objectives such as obstacle avoidance or fault tolerance or whatever it may be that the person operating the platform wishes to focus on. And so this motion control is designed for this platform so that these operators can examine these properties. So now in the presentation I'm going to be showing the failure modes that have been implemented, as well as a demonstration and video. Currently the lock joint failure is implemented. The motor controllers can give a inductive brake to each of the motors and freeze it there indefinitely, and so that can be done, and that simulates the lock joint failure nicely. The free swing failure is not implemented yet. That is a planned implementation for the future, and that can be done just by removing the power from each one of the motor controllers, and that will cause the motor to fail and gravity will pull it down. And this video shows each one of the failures. It shows the arm pointed directly at the ground, and it is going to be told to move the end of the arm directly upwards, which is not an easy task for it to do since it's in a strange position. None of the motors can do it directly, and so you'll see the control will move the end of the arm away from that point and then bring it back to that original trajectory in that original spot. And then after that it will lock the motors in place, and then I pull the power and the motors will fall. So I wanted to speak some on the programming of the platform. There are 2 options that are currently available using the Arduino environment, which uses C++. This is very naturally compatible with the Arduino, but it doesn't have as good of linear algebra. There's Eigen, there's matrix math, there's a few other libraries, but it's not necessarily the most elegant of solutions. And linear algebra is very important because the Jacobian control uses linear algebra for its matricy processing, and there are other ways that you can do that without linear algebra libraries, but they're just not as good. Of course, there's also MATLAB. Simulink is a relatively recent development for the Arduinos, and that is an option now, which comes with all the power of MATLAB and Simulink with it. So that's a great option that we'll be exploring in the future. Thank you for listening. If you're ever at Colorado State University and you want a demonstration, maybe we can show it to you. Thank you.